talk about the ideal gas law applications. So more specifically, we talk about gas density and molar mass of a gas. And basically what we're going to do first is we're going to derive an equation that relates density of a gas to its molar mass. And we can do that because we know what the ideal gas law is. We know molar mass is mass over moles, or grams per mole of the units. And we know density is mass over volume, or we use grams per liter as our density. And we'll get there by dividing both sides of our ideal gas law by the mass of the gas. And we can do that because whatever we do to the left-hand side of the equation, as long as we do to the right-hand side of the equation, it'll still be equal. And then we're going to rearrange things. So we're going to move the mass to the numerator and volume to the denominator using cross multiplying. And then rearrange, put these terms together, and put these terms together. So this term, it's moles over mass, so that's the inverse. That's 1 over the molar mass. And m over v is density. So for the molar mass in the section, we'll use kind of a script m, and that stands for molar mass. Let's add that in over here. And the units are grams per mole. And this is density. And the units of this are grams per liter. And then your temperature is in Kelvin, and your R depends on what your pressure unit is. We can also do stoichiometry with gas. And the reason why we can do this is that if the pressure and the temperature are constant, then the volume is proportional to moles. So all we need to do a stoichiometry problem, as long as we're not changing the temperature or pressure, is just know how many volumes of gas there are. When we're using pressure and temperature of like a system, a common system that we come across is the standard temperature and pressure, or STP. So at STP, which a lot of the problems you'll see that will be under STP, the molar volume, which is the ratio of the volume to moles, is constant. We can say it's constant because rearranging the ideal gas law, moving P to the denominator and N to the denominator on the other side, gives us R times T over P, where under STP, T is at 0 degrees Celsius, which remember you have to write in Kelvin, so 273 Kelvin, or 273.15 Kelvin, and P is the pressure, which is 1 atmosphere at STP. So under STP conditions, molar volume is 22.4 liters per mole. This is a good number to memorize. But you could always derive it just by plugging in R times T times over P. So here's an example. And I said that all you need to know, as long as your temperature and pressure are not changing, is the volumes of things. So under these conditions, we have 5 liters of oxygen reacting with excess methane, and we want to know how much CO2 is formed. We can't do that same idea with water because it's a gas, because it's not a gas. But basically, for every 2 gases, you get 1 gas of CO2. So if you had 5 liters of oxygen, you would only get 2.5 liters of carbon dioxide. And we can show how this works using this idea of molar volume. Because we're at STP, we know that 5 liters of any gas, we know that 22.4 liters of that gas is 1 mole of that gas. And using the stoichiometry, now that I'm in moles, I can say 2 moles of oxygen is 1 mole of CO2. And then finally, because CO2 is a gas, I can say that 1 mole of CO2 is 22.4 liters. The 22.4 liters cancel, and you end up with 2.5 liters. So this is true because we're at STP. But if we were at any other condition, not under standard temperature and pressure, these 22.4 numbers would be different. But if the initial condition and the final condition are the same, you would have some number here, you have the identical number over here, and they would cancel. And then you could just go from liters, use the stoichiometry from the balanced equation, back to liters.